Hi everyone, I'm Mike Jacoby from Lucid Vision Labs, and in this video, I'm going to talk about our Triton 5.4 megapixel camera featuring Sony's IMX490 rolling shutter CMOS sensor. Some of you might know this sensor as Sony's Automotive sensor. This is because it has on-sensor high dynamic range and LED flicker mitigation. Thanks to Triton's IP67 dust and water protection, as well as its other factory tough features, this specific Triton model is not only excellent for automotive and outdoor applications, but also any other application where you're imaging scenes in very high contrast, where you need as much details in the highlights and shadows as possible. Let's take a deep dive into how this sensor works and what makes it so special. Let's start off by zooming in and taking a look at the pixel structure. Unlike most sensors where each pixel is the same size, the IMX490 has two subpixel sizes, one large and one small, with each one having a different sensitivity. If we take a cross-sectional look at the pixels, we can see that it's a back illuminate sensor with the wiring layer below the photodiodes for better sensitivity. Each subpixel has its own different sized microlens too, to better focus light into their respective photodiodes. A light shield is implemented, as well as deep trench isolation for each pixel. This prevents optical crosstalk and leakage of electrical charges between the two subpixels. So what's the whole point of having two different subpixel sizes in the sensor? Well, first let's take a step back and look at how a traditional HDR image is made on a machine vision camera. Typically, what people will do is program the camera to take a series of exposures over time, one after the other. These different exposures are meant to capture different details in the shadows, the midtones, and the highlights, and are then processed and combined either on camera or on the host PC into an HDR image. This type of HDR works really well for static scenes where there's very little or no motion. But what happens when we have movement in the scene, such as a car moving down the road? Because each exposure in the series happens at a different time, each exposure is going to capture a slightly different scene. So when the system processes all the images together, we're going to get motion artifacts due to the time latencies between the exposures. This is where the two different sized subpixels come in. Because each subpixel has either a low sensitivity or high sensitivity, the sensor can be set to one exposure time, and the two different subpixels will capture different sensitivities in one go. Each subpixel also has two channels, one for outputting a high and low signal, effectively creating four channels with different image data. Now that the exposures happen simultaneously, the four channels can be combined on sensor into one 24-bit HDR image. In addition, this sensor also offers LED flicker mitigation. Many conventional HDR sensors use a really short exposure time to measure low sensitivity data to avoid saturating really bright areas in the scene. And these short exposures more easily capture the flickering of AC lighting at 30, 50, or 60 Hertz. But because the IMX490 doesn't need these short exposure times, thanks to the small subpixel with low sensitivity, the sensor can be set for longer exposures, capturing more data and effectively averaging out the flickering of the lights. Just a quick side note, you can actually change the exposure time of each subpixel for more advanced HDR, but it is recommended that they be kept the same. Either way, Lucid gives you the option through our Arena SDK. We also have a variety of options to tune the IMX490's output, including the option to view and save each HDR channel separately, add custom lookup tables, control the bit depth, and output the full 24-bit RGB images thanks to Triton's 24-bit ISP. Now that we've gone through an overview of the on-sensor HDR and LED flicker mitigation, let's go even deeper and look at how the sensor is actually able to produce four channels of signals. Here we're going to look at the large subpixel, SP1, and the small subpixel, SP2 potentials, and how those potentials relate to the driving sequence. At the top half of the section, we can see a cross-section of each subpixel and how each one is made of a photodiode, 2 floating diffusion nodes, and multiple gates. At the bottom is a pixel driving sequence where exposure happens simultaneously, but readout happens serially. We'll start with exposure, where both subpixels are exposed at the same time. Then, SP1's reset levels for low and high conversion gain are sampled. Following that, the signals for high conversion gain and low conversion gain are then sampled. Sampling both the reset and the signal allows SP1 to perform correlated double sampling, CDS, for noise reduction. Then we move on to sampling SP2. SP2's high signal is sampled first, then SP2's low signal is sampled second. No reset levels are read before SP2's high and low sampling. Instead of CDS, delta reset sampling is performed. Let's see it again without any pauses. Alright, that's it for this video. We really just wanted to take a closer look at what benefits this sensor has to offer with the sensor's unique 2 subpixel design and its ability to capture HDR images without motion artifacts along with LED flicker mitigation. Pairing that with Triton's IP67 protection and factory tough features, it makes for a very robust and cost-effective 5.4 megapixel camera. Well, that's it. Thanks so much for watching and stay lucid.